Thank you very much. Thanks, Kane. I'm Matt Bradbury. I'm from the Solution Engineering team. And I'm going to start with a declaration. And my declaration is, I love designing CorDapps, which is convenient because that's my job. But I'm also going to make a second assertion that if you're here at CordaCon DevDay, you probably like doing this stuff too, or at least a reasonable proportion of you like doing it too. So this is all about how to help you design better CorDapps, or at least find it easier to design the CorDapps you're working on. Everybody likes it. However, designing CorDapps has changed somewhat since when we started doing it in 2017, when we started doing all this fun stuff. We're not really doing, well, most of us are not doing POCs anymore. Now it's all about getting to production-grade applications. And by their very nature, production-grade applications are more complex. They need more functionality. They need to include inconvenient things like the non-happy path routes through the functionality. Privacy is massively important. A few other talks over here talking about how we work, how we make sure that we maintain privacy when we build these applications. And designs must be provably robust. So I'm going to make an assertion, and that assertion is, it would be, I'm going to say we need, but it would be nice to have a way to represent and reason about non-trivial CorDapp designs. And that's kind of where we're heading with the CorDapp design language. So how do we represent, or how have we represented in the designs in the past? Well, I did a little bit of archaeology on our wiki site and went back 3 years and had a look at how we've done it. And there's lots and lots of different ways to do it, but they're all different, and they all don't quite hit the mark very well. But then they're not bad. Unfortunately, what normally happens is this is what the CorDapp design looks like, which is how most of the CorDapp designs get discussed. Pretty difficult to follow. And just to take a kind of a semi-real client example, this is from a genuine client visit a couple of years ago. I've redacted some of it to protect Alessandro's identity. Where is he? He was meant to be in the room for that jibe. He drew this diagram when we were talking about how to structure the application they're working on, and we had various people standing around it. And they all kind of had a different point of view. So one of them was saying, oh yeah, I see that. I see, so it's all contained in the same Corda state. That's great. Unfortunately, somebody else looking at exactly the same thing was going, oh, I see. It's all split across multiple Corda states. And they had another guy who was going, I have no idea what that box is meant to be. And they had another guy who was more interested about what's for lunch here. And by the way, I was this guy and that guy at the same time. But anyway, the whole point is, it's to borrow another thing from Corda, that what you see is what I see. In this case, what you see is not what I see, because we're all looking at something and we're all interpreting something different. And the problem I kept seeing was we spend half our time working out the idea, the concept in our head, but we spend the other half of the time trying to work out how actually to write it down in a way that other people can comprehend what we're talking about. So I'm going to modify that first assertion I made and said, actually what we need is a standardized way to represent and reason about non-trivial Corda designs. But also I'm going to stick a rider on that. We want one which encourages good CorDapp design as well. And that is what CorDapp design language is all about. By the way, previously it was called Corda Modeling Notation, but so CMN, when Corda Enterprise Network Manager came out, it all got a little bit confusing and marketing banned me from using that, so I had to come up with a new name. So there it is. So let's have a look at what we're trying to achieve with CorDapp design language. So first and foremost, it needs to allow you to represent accurately and clearly non-trivial CorDapp designs. So stuff when it starts to get a little bit more complicated than the basic stuff. In particular, we need to be able to talk about the shared data and state that Corda applications have, the shared logic or shared functionality or shared rules, really. We need to be able to add things about permissioning, so who signs what to give their consent to things. And the thing which I always bang on about repeatedly, how do you make sure that your CorDapps operate in a way where you're preserving your counterparty's privacy? It also needs to encourage good design. Just to explain what I mean about that, R3 is a very generous company. In fact, when we give you Corda, we give you two products, really. The first one is what I call the ledger layer. So this is smart contracts, this is transactions, this is states and rule books and kind of guaranteed logic. But we also give you this really cool thing on top of it, which is the flow framework or the orchestration layer. And that allows you to communicate with your counterparties and do these quite complex process flows to make things happen. And that's great. But if you mix them up, you can get yourself into trouble. If you start putting controls over what people should do in the flow layer or orchestration layer, you start building CorDapps which can get hacked when people can hack their flows and things like that. So this notation is designed to make you think very clearly about the distinction between those layers. Also, having a standardized way to write things down also leads you to be able to write standard reusable design patterns, which is helpful because it makes people don't have to reinvent the wheel every time. It should degrade gracefully, and I'll give you an example of what that means, but some of this stuff you're going to see on the screen gets pretty hairy. There's a lot of stuff on there because it's a full specification language, effectively. But you don't have to use it every time. We want it so you can pick bits and do much simpler diagrams which still retain their accuracy and truth, if you like. And then the last one is it's not marketecture. Well, it's not just marketecture. So marketecture is a word which Adam Fergal very kindly made up to take the piss out of me. There he is. He's basically drawing pretty pictures for marketing materials, which is a super important thing, and R3 excels at as well. This is not just marketecture. This is a proper design language. You can use it as marketecture, but actually you should be able to take this stuff and you should be able to turn it more or less directly into code. Cool. So that's what we're trying to achieve. So what am I going to take you through? I'm going to show you by example. I'm going to dream up a use case, create a smart contract, or describe a smart contract, show you some smart contracts in action, and then show you the privacy overlays. And you'll see a few design patterns along the way, which will be helpful in themselves, hopefully. Okay, so first bit, how to represent a smart contract. So a bit of a definition first. What do I mean by a smart contract? Because that's not normal terminology in Corda world. It is in things like Ethereum or other blockchain platforms. But a smart contract in Corda is really the combination of your contract state, so your data set, possibly with a bit of functions on it, and then your contract, which is your rule book. When you combine those together, you effectively get a module of functionality that has defined, constrained behavior. And that's what I mean by a smart contract in this case. And a good way that I've found of thinking about a smart contract is to think of it as a finite state machine. So those of you who've done computer science or electronics or something may be familiar with a finite state machine. It's a thing that can be in different states, and you're allowed to do different things when it's in different states. So the classic example is a washing machine. If you have a washing machine, it can be a state, I am full of water, and when it's full of water, you're not allowed to press the open door button. It won't let you do it. If you run another thing that you can do, which is empty the water, then you're in a different state. You're in the I am now empty, and now you can run the command which allows you to open the door. And everybody's happy, and everybody's kitchen floor doesn't get involuntarily cleaned. So let's take an example. Let's think of some generic agreement. It's as simple as you can get. There's a seller sending goods to a buyer for an agreed price. What I'm going to show you now is the state machine view out of the CorDapp design language, or how to draw a smart contract. It's kind of the less technical name. Okay, so let's have a think about the different states that this contract can be in. First of all, a little bit I can't say that word. State is overloaded in CorDapp language. So I'm going to change it from a finite state machine to a finite status machine. You'll see why, because, well, hopefully you will anyway. So we have agreement state, which is my kind of contract state thing, but each of these can be in a different status. So my agreement state can be either in the status draft, status agreed, or status cancelled. So those are the three different statuses it can have. So how do we kind of move between those? Well, we need some transitions here. We need to be able to create the draft. Once we're in draft, we need to be able to modify it. Then at some point, we'll want to agree it, modify it, and then cancel it. Now, this is fine, but you need to kind of make the mental shift into what we're actually saying in Corda here. Each one of these arcs is effectively the command for a transaction. And at the beginning of the arrow, we're saying this is your input state. At the end of the arrow, we're saying this is your output state. So when we look at this arc, we're saying we have an input state, which is status draft. We use the agreed deal command, and then we end up with an agreement state, which is the status agreed. So what this is giving us is a map of all the different things you can do with this agreement state, how you can move around, and what you're doing when you're moving around. Okay, and the way this turns into the code is these are effectively a set of constraints. You're constraining the contract, the smart contract, and saying you're not allowed to go from draft over to cancel because there isn't a legitimate transition. So you take this and you turn that into the code which sits in your verify contract and says, I'm only allowed to make certain transitions in certain cases. Okay, so that's one type of constraint, but in a contract you want to be able to constrain it in many, many more ways than this. The next one to think about is when we have these transactions, they need to be signed, so we need a way of saying who should sign it. And the way we do that is by adding a signing constraint, and this is the kind of effectively this language is all about having kind of shortcut annotations so you can put an idea down in a consistent way. So here we're saying, okay, when you're doing your draft stuff, creating it or modifying it, anybody can sign. It doesn't really matter. It's just a draft. Who cares? However, when you're at the point where you need to move from draft to agreed, then actually this is a proper legal, or maybe a proper legal deal. So both the buyer and the seller need to sign it. Okay, so that's kind of signing constraints. Next, we want a way to be able to say, well, what's in this state? So these are just data classes. They have properties. We want to be able to, so we just stick them in the box effectively. Now, agreement state inherit from contract state. Contract state has participants. Participants are important in Corda because they are the people who this transaction will get distributed to upon when you call the finality flow. So we need a way of saying these are the participants. So some more constraints. We want to be able to specify what makes a good state. So we have, what we're talking about here is state level constraints. So these are things that say this is a well-formed state. So in the example we've got here, all the fields must be completed except the cancellation reason. So you're putting something in your verify function that says if you haven't filled in them all, this is not a valid state, therefore reject the state by rejecting the contract. Next type of constraint is constraints which attach themselves to the thing you're trying to do, or your, we call them transaction level constraints. So when you do the agreed deal, you may want a different set of rules from when you do the modified deal. So you need a way to be able to express those command-specific points. Next one, visibility constraints. So this is super important when you start thinking about privacy. You need to be able to articulate who's allowed to see what. If you do a design which sends all of this information off to your business network operator, that's not okay because this is saying business network operator is not allowed to see it. And then the last one to complete the set is the multiplicities. If you think about a cache contract, it doesn't matter how many input states you have and how many output states, as long as you're not creating cache, it's all fungible. But sometimes you don't want that. Sometimes you want to specify that you've got a one in and a one out. And this is what this notation here does. One in, one out. The M is saying it also must be matched, so your linear ID must be the same, so you can build a linear chain of states as well. Okay, so that's the basic picture of a smart contract. And the idea of doing this is you can communicate what you're thinking, communicate what you've designed, whatever you want to do. But it also allows you to ask some questions. So let's say we go into a review session and somebody goes, hang on a minute. Complication number one here. That's not a true agreement of two parties. because the way Corda works is your initiator can decide, I want to initiate this transaction, but your responder, there's no human interaction with flows. The responder doesn't get to make a conscious decision about whether they sign it or not. They just sign it. So actually this looks like a good setup, but it's not quite. We need to add something else. And it so happens there's a pattern for that. I haven't got time to go through the details of the pattern, but we can do something where we add the requirement in each of these transitions, each of these commands, to say, actually, this is not okay unless I see some sort of permission, or I've called them propose and consent tokens, which are included in the same transaction. So you always got a pre-permission, which allows people to make that transition. So you can start to articulate that. And in fact, I'll give you a little bit more detail on that. I'm going to use a different view. So if that was a state machine view, this is the transaction instance view, or basically just draw a picture of a transaction. This is quite an obvious one. So the pattern we're looking at is trying to work on this agree deal transition from draft to agreed. So it's the same thing we're just looking at. But then you can express this particular pattern as a series of sequential transactions. So the first transaction is generating a proposal. I would like to do this transaction, and it's signed by one party. The next one is looking at a proposal, saying, yes, I consent to that proposal, and then signed by the other. And then your verification function only allows this to pass if you have these two states in them. So that's an interesting pattern in itself, which you might want to cogitate on. But what I really want to show you is this is another way of representing how a smart contract kind of in action, basically drawing pictures. This is the one that's closest to the material we have on the doc sites and key concepts and stuff. Okay, complication number 2. The business network operator would quite like to be paid for all these services. So they want to charge every time a deal is initially agreed. So what we're going to say is, okay, we need another modification here. We need to add another constraint when there's an agreed deal that we require a billing token. Okay, that's great. Let's use a different view, state evolution view, or state machines in action, to show how the pattern for billing may build up. Okay, here we are. We've got our agreement going from draft to agreed. This is an example of it degrading gracefully, by the way. You don't have to have all of that detail. You can just say, here's a state in this status, here's some data set, and here's the participants who were involved in it, as a slight aside. Okay, so we've got the agreed deal. We've got some billing state, and this billing state will track spending. And the rules of this agreed deal say, I'm not going to let this happen unless I see somebody spending the 100 units or whatever it is. And that's great. We also need a way to say it's in the same transaction. So we put a box around it and just say these two things are happening together. Okay, that seems fine. Let's have a think about the next transaction. Separate deal, still with party A, but now it's with party C. And party B and C are competitors potentially. So that billing state got created here. We'll now hop into this transaction and get consumed here, increment by another 100, and power or pay for this transaction. Woohoo, we've got a billing solution. However, if we put a privacy overlay over the top of it, we can start to spot some problems. Let's think about what the B&O sees in this. B&O is a party on here. We can start tracing back what the B&O gets to see. B&O is a participant here. That means B&O gets to see all of this transaction. That's not okay. The rules earlier said that only these people are allowed to see it, so we have a privacy leak. Likewise, when this input state gets resolved, they see this transaction, which is also not okay, so it's another privacy leak. You can take it from party C's point of view. Party C sees this transaction, okay, but party C resolves this transaction to check the provenance of this state, and then they get to see it, so it's another privacy leak. So this naive example of how to do billing can quickly get into a situation where party C ends up with party B's private data in their vault. And just to ram the point home, this is not okay. If you design a CorDapp like this, somebody's going to start looking at the logs and going, why the hell can I see everybody else's data in it? But you can see how if you did the naive implementation of a CorDapp, you could accidentally fall into this sort of trap. So it's not okay to pose a problem without a solution. So let's do this again a different way. Again, using the same view, but hopefully showing that it's solvable. We have the agree deal here. Okay, this is what we want to pay for. We have the box. But this time, let's pull the billing state out of the transaction and put it somewhere else. So B&O issues this billing state. B&O increments, proving that this money has been, the usage has been monitored. But at the same time, we do a cunning little thing. We create a receipt for that increase of 100. And it's the receipt which we put into this transaction, or the billing chip that we put into that transaction. What we can do there is we can say, this agreed deal will only be allowed if we see a billing chip for the right amount of value. And we can do that again with transaction 2. We increment our kind of cumulative tracker, and then we have a receipt which powers this transaction. And then at some point, that billing state goes off to the B&O so they can raise a real-world invoice. OK, so why is that cool? Well, why is that hopefully cool? Well, let's do the privacy analysis this time. We can think about it from the B&O's point of view. They end up with this thing which tells them they've got to go and bill somebody for 200 units. But when they resolve this transaction, they see this billing chip, but they don't get to see all of this transaction. Likewise, when they resolve this, they see this billing chip, but they don't get to see all of this transaction. So effectively, the B&O knows with certainty these deals have taken place, and knows with certainty that they can bill for this, but they don't know anything about the transactions that took place. Likewise, if we think about what happens with party C, they see this billing chip, they resolve it through to this transaction, but they don't have any information about their competitor's deal. So effectively, by modeling this, analyzing the privacy, we've tweaked the way we do things from the naive approach to a more sophisticated approach, I suppose, and we've built something which hopefully safe. And of course, the point is not only just to the point of saying this is not just to show you the pattern, it's to show you how we've expressed the pattern in the modeling language. Just a few takeaways, because I went through a lot of stuff pretty quickly. CorDapp design language is here to help you write better, more robust CorDapps. It allows you to describe complex production-grade smart contracts. It allows you to show kind of smart contracts in action, so that when we were tracing it through and seeing how the billing all worked. It allows you to reason about privacy, super important for the reasons I've just been through. There's also some other views as well which are available, which I haven't gone through because 25 minutes is nowhere near enough time to talk about this properly. But if you want to know more, there's a lot of detailed information and building through the kind of theory behind this on our Corda Solutions doc site. If you just type Corda Solutions in Google, it'll come up. And this section here is taking you through the overview and the details. And then the last thing to say is we're going to be publishing a Corda design language template so you don't have to make all the shapes up yourself. OK, that's everything I have. Thank you very much for listening. Cool. Hopefully no time for awkward questions now.
I think you might have one. I apologize.
Oh, that's perfect.
OK, the first one is, if the participants are mentioned, then why have a visibility constraint in the state machine view?
They're two different things. I'm not going to be able to click through 60 slides to get back to where it is. Or can I? So this is just a statement of who the participants are. This is much more about saying who's allowed to be in the transaction. So, and this really comes to play when you've got more than one state machine interacting with it within a transaction. It wasn't super explicit earlier, but on those billing examples, you had this state machine, but you also had a billing state machine interacting at the same time. And the instances of those two state machines came together in the same transaction. When this is kind of looking beyond the single state machine to the rules which need to apply when it's within a transaction with other people. So it is the funny one out of all of them, but and it doesn't necessarily go directly into the contract code like the other constraints do. But it is important to be able to specify it, because when you're looking at these things interacting with each other, that's when you start to potentially break those visibility constraints. Hopefully that answers whoever was kind enough to give me that slightly difficult question.
You actually had a bunch of more questions, but unfortunately we ran out of time. So if anyone does have any more questions for Matt, I think he'll be around.
Of course, yes.
So yeah, feel free to grab him.
This is my favourite subject. I'm very happy to talk to anybody about it.
Oh,
cool.
But thank you.
Okay, thank you very much.